Okay, let's look at some of the basics of hypothesis testing, all right? Now, in statistics, a hypothesis is a claim or a statement about a property of a population. A hypothesis test is a procedure for testing a claim about a property of a population. So, for instance, we might want to test a claim about a population mean, or a claim about a population proportion, or a claim about a population standard deviation or something. So, we're going to conduct hypothesis tests to test those claims, or tests of significance. Okay, now in order to do a hypothesis test, we want to look at some of the parts of a hypothesis test. The first thing you do when you are going to do a hypothesis test is you set up the hypothesis, and there are two hypotheses. And the first one is the null hypothesis. And the null hypothesis is denoted HO, like we see here. Null hypothesis is denoted HO, and it is a statement that the value of a population parameter is equal to some claimed value. So we're making a claim that a population parameter is equal to some value. Um, the other kind that we can do is the other kind of hypothesis is the alternative hypothesis. And the alternative hypothesis is denoted in one of these three ways: H1, HA with a lowercase a, or HA with an uppercase a. All three of these notations mean the alternative hypothesis. And the alternative hypothesis is the statement that the parameter has a value that is somehow different from the null hypothesis. So that means we're going to either say that it is less than the hypothesized value, greater than the hypothesized value from the null hypothesis, or just plain not equal. These are the three different um, things that we can use for symbols that we can use for alternative hypothesis. And notice that the null hypothesis is a claim about equality, so the null hypothesis will be equal. You'll always use an equal sign for the null hypothesis. And the alternative hypothesis, you use one of these three inequality symbols. One of these three inequality symbols. So um, you can always identify the null, which hypothesis is the null and which one is the alternative, by where the equal sign is. If the equal sign is on the claim, then the claim will be the null hypothesis. If the equal sign is on the is not on the claim, then the claim will actually be the alternative hypothesis. All right, so let's take a look at some creating some hypotheses. Okay, so here we have identifying the null hypothesis and the alternative hypothesis. In exercises 9 through 16, examine the given statement, then express the null hypothesis HO and the alternative hypothesis H1 in symbolic form. Be sure to use the correct symbol. So we're going to be making statements about either a mean. If we're making a statement about a mean, we use mu. A proportion, in which case we would use p, or a variance, or a standard deviation, in which case we would use sigma. All right, so these are the three parameters that we're going to be making claims about. Number 10, the proportion of people aged 18 to 25 who currently use illicit drugs is equal to 0.20, or 20%. All right, so let's see. What that is a claim about a proportion, right? It says right here, the proportion. This claim is that the proportion of adults, P, the population proportion, or the population of people aged 18 to 25, sorry, the proportion of people aged 18 to 25 who currently use illicit drugs, and it says is equal to, so is equal to is definitely equality, and it's equal to 20%, zero point 0.2. So 20%. Well, this is the claim, but we also need to identify it as either the null or alternative hypothesis. And all we need to look for to see which one it is we need to look for the equal sign. If there's an equal sign, then it's definitely the null hypothesis. If there's no equal sign, then it's the alternative hypothesis. So in this case, the null hypothesis is actually the claim. So the alternative hypothesis, you find the alternative hypothesis H1. So the alternative hypothesis H1, let's see. The alternative hypothesis would be, uh, let's see, the proportion, that the proportion is somehow not equal to 20%, because no other statement is made other than that it is equal. So the alternative to being equal is to be not equal. This is the alternative hypothesis. All right, so now let's take a look at number 12. Number 12 says the majority of college students have credit cards. Now this one is kind of tricky because they don't really tell us what parameter we're trying to make a claim about here. So we have to use a little bit of intuition to realize that when they say the majority of something, they're talking about a proportion. And a majority is actually a proportion that's greater than 50%. So the claim that's being made here is that the proportion of college students that have credit cards is greater than 50%. So a majority means that the proportion is greater than 50%. Okay? So if we're saying that this is the claim, then we have to identify the claim as either the null or alternative hypothesis. But this is definitely the claim. And in this case, this claim does not contain the condition of equality. This is saying that the proportion is greater than 0.5 or greater than 50%, which does not contain equal to 50%. So we'll say that this claim has to actually be the alternative hypothesis. So this claim is actually H1, and the null hypothesis is always the claim of equality. So the null hypothesis is that P, the proportion, is equal to 50%. All right. So in this case, it turns out that the null hypothesis is not the claim. So you can't assume that the null hypothesis is always going to be the claim. Sometimes the claim is actually the alternative hypothesis, and it all depends on whether it contains the condition of equality or not. Now let's take a look at number 16. The mean weight of plastic discarded by households in 1 week is less than 1 kilogram. Now this one is a claim about a mean weight, and it's saying that the mean weight is less than 1 kilogram. So the mean weight. So in order to make a claim about mean, or we're making a claim about actually the population mean, which is mu. So in this case, we're going to use mu instead of P in order to form our null and alternative hypothesis. So mu, this claim is saying is less than 1 kilogram. The population mean is saying, right in this statement, is less than 1 kilogram. All right, this is the claim. This is definitely the claim. The mean is less than 1 kilogram. But this mean is also an alternative hypothesis. This is an alternative hypothesis. Oops, I said alternative, but I wrote null. So let's get rid of that. This is definitely an alternative hypothesis, H1. And the null hypothesis, once again, is the claim of equality. So the null hypothesis is that mu is equal to 1. All right? So here, this is how we are going to form our hypothesis, null and alternative hypothesis. We'll identify the claim that is being made. We'll write it in symbolic form using one of the correct forms here, using the correct parameter. For means, we will use mu, and for proportions, we will use p, and for standard deviations, we will use sigma. All right? So that's how we are going to identify our null and alternative hypothesis. All right, the next thing I want to talk about is critical values. All right, so let's talk about critical values. And first, we need to talk about critical regions. The critical region or rejection region is the set of all values of the test statistic that cause us to reject the null hypothesis? Well, the test statistic we're going to get from the sample. So basically what we're saying is we're going to get a number from a sample, and if that number from the sample is in this set of values, it's going to cause us to reject the null hypothesis. That's why it's called the rejection region. For example, see the red shaded figure in figure 8.3. Well, these are the red shaded figures. This would be a rejection region right here. This is a two-tailed rejection region, and this is a one-tailed rejection region, but we'll get to that in a second. All right, the significance level, which is denoted by alpha. We've seen alpha before. We know that alpha is also 1 minus the confidence level, right? But the significance level denoted by alpha is the probability that the test statistic will fall in the critical region. So basically, this red area, the area over there, that red area is the significance level, and it's alpha. And actually, in this case, it would be alpha over 2, depending on this over here would be alpha over 2, this over here would be alpha over 2, so the whole red area would be alpha over 2. So the significance level is actually the probability of falling into the critical region. Okay, it's the probability that the test statistic will fall into the critical region. All right, and if the test statistic falls in the critical region, we reject the null hypothesis. So alpha is the probability of making the mistake of rejecting the null hypothesis when it's actually true. That's actually called a type 1 error. All right? This is the same alpha we introduced in section 7.1, 1 minus the confidence level. All right, a critical value. A critical value is a value that separates the critical region from the values of the test statistic that do not lead to rejection of the null hypothesis. So the critical value actually depend on alpha. And if you look here, let's see, the critical region would be, this would be the critical region. These areas over here, these tails would be the critical region. This would be a critical region over here. That would be critically low. And this would be a critical region over here. That would be critically high. So those are the critical regions. The critical regions, all right? Now the significance level is the area within those regions, the red part. And actually, the critical value is the important thing. The critical value, once again, that's the same thing we introduced before. But we're going to expand it a little bit. The critical value is now the z-score that separates the critical region from the non-critical region. Basically, the critical value separates the usual values from the unusual values. The unusual values are over here. And the probability of getting a value this high is going to be the critical z up here, the z of alpha over 2. And the probability of getting, or sorry, the value that separates the extremely low values from the extremely high values is over here. This is negative z of alpha over 2. And once again, this one separates the extremely high values from the normal values. This one separates the extremely low values from the normal values. All right, this one would separate the extremely low values. And because there's only one thing over here, there's only one critical region, we call that one tail. This is a one-tail test because there's only one critical region. So alpha is all over here. This is all of alpha over here. See, this red area over here is only alpha over 2 because we have to divide alpha in half. So alpha over 2 goes over here as an area. The area of this region is alpha over 2. And alpha over 2 goes up here. So the area of this region is alpha over 2. The probability of falling in that region is alpha over 2. This here is the z of alpha because there's only one critical region, one tail. So these are the different types of tests. There's another one-tail test over here also. This is the z of alpha over here, the z of alpha, because this area over here is alpha. That's a probability of alpha falling in that region. So these are the types of hypothesis tests. A two-tail test is the kind of test we have up here. See, there are two rejection regions, two tails. A left tail test is what we have over here. And I guess we lost the graphic for the right tail test. But the right tail test would be another bullet, right tail test. The right tail test is the critical region on the extreme right. The critical region is on the extreme right. So a right tail just means the critical region is on the right. A left tail just means the critical region is on the left. Those are both one-tail tests. And a two-tail test means you have critical regions on both sides. All right, now how do we identify what kind of tail we have on our test? Well, let's see here. Let's go ahead and find critical regions here. All right, well, finding critical values. In exercise 17 through 24, assume that the normal distribution applies and find the critical z-value. All right, when we're finding critical values, what we want to do is we want to look at the number of tails, all right? For a two-tail test, like we have up here, this is the two-tail test up here. And for a two-tail test, what we want to do is we actually want to take alpha. We want to divide alpha in half because we want to put half of alpha in this tail, and we want to put the other half of alpha in this tail. So over here will be alpha over 2, and over here will also be alpha over 2, and we'll put half of alpha in each tail. So for a two-tail test, we're actually going to find alpha over 2, find the z-score for that, and once we find the z-score for that, that will be the critical value that separates our critical region from the usual values. So we're finding alpha over 2 to be 0.05. And what we're looking for is we're looking for the z-score that separates 0.05 in the left and right tail, so that the entire probability or the entire area in the total area in both tails will be 10% because we'll have 5% in each tail. So what we're doing here, we're looking for the z-score that separates 5% up here, 0.05, and 5% down here, 0.05. And because this thing is a symmetric distribution, whatever number we get up here for the z of alpha over 2, this one will be its opposite. So we only need to find one. The positive one will correspond to the negative one. So we need to find that z-score. So let's pull out our TI. And what we're going to do is we're going to find the z of alpha over 2, which is the z-score here. So let's see. So we're going to go to second distributions. We're going to go to inverse norm, and we're going to put in the area to the left here, which is 0.95, because remember, into the inverse norm, we always have to put the area to the left, and that area is 0.95. We press enter, and we get 1.64. So this is equal to 1.64, which means this one is equal to negative 1.64. So here are the critical values for our two-tailed hypothesis tests. We have a rejection region on each tail. So any test statistic above 1.64 is going to lead us to reject the null hypothesis, and any test statistic below negative 1.64 is going to cause us to reject. But any test statistic in this region here is a usual value, so we will fail to reject the null hypothesis. All right, that's how this is going to go. We're going to use these critical regions to determine what we should do with the null hypothesis. So let's see. Let's calculate the next one. So down here, let's see. Alpha in this case is equal to 0.01, and we have the alternative hypothesis. The alternative hypothesis is that p is greater than 0.5. Now, why do they tell us that? Well, the alternative hypothesis is what actually tells us where the tail is. If you look at the inequality symbol in the alternative hypothesis, the inequality symbol in the alternative hypothesis will always point at the tail. And if it's not equal to, if the alternative hypothesis contains this symbol not equal to, that just means it's two-tailed. It's pointing at both tail, because this actually not equal to actually means you're less than or greater than. You're one of those two, so you're pointing at both tails. That's what not equal to actually stands for. All right, because, all right, now let's see. So what this is a right tail test. See, the alternative hypothesis is that p is greater than 0.5, so we're looking for extremely large values. We're looking for extremely large values of p, and those are going to be unusual. We're looking for unusually large values of p because it's a right tail test, because the alternative hypothesis is greater than, and it's pointing to the right tail. We want the entire area to be alpha over here. So we want all of alpha over here. We don't have to divide alpha by 2 when we're doing a one-tail test. If it's a right tail test or a left tail test, you have to find the z of alpha, not the z of alpha over 2. Only for two-tail tests do you find the z of alpha over 2. That's why we did it for the last problem. So we don't need to divide alpha by 2. All we have to find is the z-score that separates the top 1% from the bottom 99%. So let's go ahead and find that. Trusty TI again. Turn it on. Let's clear this one. Actually, we can, with the TI calculator, you can actually find the last entry by doing second entry, and it'll, oops, we do second enter, and it'll put the last thing we put into the calculator up there, so you don't have to go through all the steps. And here's the inverse norm function. And what I want to plug in is I want to plug in 0.99. So this is the inverse norm with 0.99, and then we press enter. So this number is actually 2.33. So this 2.33 is the critical value. It's the value that separates the rejection region or the critical region from the usual values. If we get a value over here, we say that's not unusual. If we get a value over here, we say it's extremely large, and that would cause us to reject the null hypothesis, all right? And the last one here is a left tail test. So let's look at that one. It actually says it's a left tail test. Left tail test corresponds to an alternative hypothesis that contains the less than symbol. Two tail test, the alternative hypothesis will contain the not equal to symbol. All right, so now let's go ahead and find the critical region, or the critical value here, the critical z. All right, so it's a left tail test. So let's draw that picture. Left tail test, which means the alternative hypothesis is less than. It's a standard normal distribution, and we're looking for the z-score here that has an area of 0.10 to the left, 10% to the left. All right, now this is very easy to do because our TI-83 calculator actually only takes the area to the left, so we don't actually even have to subtract this from 1. And this is actually going to be a negative number because it's on the left. So we're looking for the area on the left, and that means when I plug it into my TI, let's see, we can do second entry again to get that last z-score we just entered. And in this case, we're looking for an area to the left of 0.10. And we press enter, and we get negative 1.28 for our critical value. So that separates the unusually low values from the usual values. So the usual values wouldn't warrant rejecting the null hypothesis, but the unusually low values would cause us to reject. That's why this is called the rejection region. Reject the null hypothesis, all right? We always refer back to the null hypothesis. All right, now we've been talking and talking and talking about this test statistic, and if it falls in the rejection region and all this. Well, these are the test statistics. The test statistic is a value used in making a decision about the null hypothesis. These decisions we're making are always about the null hypothesis, okay? The test statistic is found by converting a sample statistic, such as the sample proportion, or the sample mean, or the sample standard deviation, p hat, x bar, or s. And we're going to take that value and we're going to convert it to a z-score. So the test statistic is just a z-score. Just like the critical value was a z-score. Notice these critical values we use were z-scores. And actually, sometimes we actually convert it to a t. Sometimes we use z, sometimes we use t. And actually, for standard deviation, we use a chi-squared. We're not really going to look at the chi-squared, but we're going to look at the z, the standard normal distribution, and the t, the student t distribution. Those are what we're going to use for test statistics, for means and for proportions, respectively. Not respectively, for means and proportions generally. So for proportions, we'll always use z, but for means, we'll either use z or t, depending on whether we have sigma or not. Sometimes we have to use t because we only have these sample standard deviations. All right, so these are the test statistics that we're going to use in this chapter. All right, now let's go ahead and try to find some test statistics. Okay, finding test statistics. In exercise 28 through, or 25 through 28, find the value of the test statistic. So we have here number 28, seat belts. The claim, now we're looking at the claim, is that more than 75% of adults always wear a seat belt in the front seat. And this is a Harris poll of 1,012 adults, resulting in 870 who say that they always wear seat belts in the front seat. So here's the claim. The claim, the claim is that more than 75% of adults wear seat belts when they're in the front seat. That's a claim about a proportion, P. So this is a claim about a population proportion. And we're saying that more than, notice we're saying more than 75%, more than 75% of adults. So this is a claim that the proportion is greater than 0.75. This is our claim. This is our claim. All right? And this is actually an alternative hypothesis, okay? This is an alternative hypothesis. Now, the null hypothesis is then that P is equal to 0.75, because remember, the null is always equality. And now we are going to find our test statistic, okay? These are the claims. We're assuming that the null hypothesis is true to conduct this statistic. So we're assuming that the proportion is actually 0.75. 870 is actually the number of people who say that they always wear their seatbelts in the front seat. And 1,012 is the total number of people surveyed. So actually N is equal to 1,012. And the number of successes, or the number of people who say that they always wear their seatbelt, the number of successes is 870. So here, this is how we're going to calculate p hat. So we need p hat and p in order to find our test statistic. Because if you notice, our test statistic for proportions involves p hat, p, and n. We have all of those things now. Let's see, well, let's calculate p. All right, so the p-value is 0.860. All right, so now we have everything we need. We have p hat, and by virtue of that, we also have q hat. So we have p hat and q hat, because q hat is actually 1 minus p hat, and 1 minus 0.860 is equal to 0.14. All right, so 0.14 is q hat. We have everything we need to calculate our population, our test statistic for our proportion, for our hypothesis test about proportions. All right, let's see. So this says that for a test for proportions, the test statistic is p hat minus p over the square root of p times q times n. We don't actually need q hat, we need q. So let's go ahead and calculate q. Q is actually 1 minus p. So q is what we need. Q is equal to 1 minus 0.75, which is equal to 0.25. So now we're going to calculate the test statistic. The test statistic is equal to p hat minus p over the square root of p times q over n. So let's see. P hat we found to be 0.86 minus minus p, which is 0.75 divided by the square root of p, and p is 0.75 times q. Q is 0.25, 0.25 divided by n. And in this case, n is 1012. So we have, uh, this is going to be our test statistic. So let's do that calculation. All right, so we have a TI-83, and what we're doing is 0.86, 0.86, I put that in parentheses, minus 0.75, 0.75, close the parentheses, divided by, and then I have the square root, so I hit second square root, and then I have 0.75 times 0.25 divided by 1012. And I close that last parenthesis for the square root. Press enter, and my z-score, my test statistic is, oops, my test statistic is 8.08. So that's 8.08. 8.08 is my test statistic. And if you remember, we said earlier that most values fall within 2 standard deviations of our, most values fall within 2 standard deviations of the mean. And the z-score of 8.08 means you're actually 8 standard deviations from the mean. So I think no matter how we cut it, this is going to be an unusual value because it's 8 standard deviations from the mean. All right, so that's how we calculate a test statistic for proportions. All right, now let's see how we deal with p-values. P-values, all right. Now, a p-value, or the p-value, is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. Assuming that the null hypothesis is true, though, p-values can be found by finding the area beyond the test statistic. So if we just find the area in the tail beyond the test statistic, we can say we have found a p-value. The procedure for finding p-values is given in figure 8.5. We have that figure down below. All right, so the critical region and the p-value method are 2 different methods, actually. All right, the p-value for a left-tail test is the area to the left of the test statistic. The p-value for a right-tail test is the area to the right of the test statistic. And the p-value for a two-tail test is twice the area in the tail beyond the test statistic in whichever direction. If the test statistic is negative, you go to the left. If the test statistic is positive, you go to the right. All right, so let's find some p-values down here. Oh, and by the way, we can use the p-value to reject or fail to reject the null hypothesis. The null hypothesis is rejected by the p-value if the p-value is too small, because the p-value is the probability of getting a value that extreme. So if the probability of actually getting a value that extreme is very small, it means that your sample is actually an anomaly, or your assumption about your null hypothesis is wrong. And we don't see that many anomalies, so it's better to guess that your null hypothesis is wrong. So the null hypothesis is rejected by very small p-values. And here's a little saying that Shriola likes. He says if the p is low, the null must go. If the p is high, the null will fly. All right, so if the p-value is too low, we toss out the null hypothesis. If the p-value is high enough, we keep the null hypothesis. So here's how we find p-values now. So that's how we use the p-values. Here's how we're going to find them. Finding p-value. All right, in exercise 29 through 36, use the given information to find the p-value. Here's table 8.5 that we're talking about here. And we're going to use a 0.05 significance level. Alpha is the significance level. We're going to use a 0.05 significance level to state, um, we're going to use a 0.05 significance level and state the conclusion about the null and alternative hypothesis, either to reject the null hypothesis or to fail to reject the null hypothesis. And we're going to do all that based on the p-value. So the p-value tells us what to do with the null hypothesis. Okay. Okay, so number 30 says the test statistic is a right-tailed test, or the test statistic in a right-tailed test is z equals 2.50. So we have a test statistic in a right-tailed test. Let's see. A right-tailed test for significance. Uh, the rejection region, or sorry, not the rejection region. The p-value is going to be on this side. We're looking at a right-tailed test. And the z-score here from the test statistic, the z-score, the test statistic is equal to 2.5. Let's look at this figure to find the p-value. Start here. What type of test? Well, this test, it says, is a right-tailed test. So a right-tailed test. We follow this one, right-tailed. The p-value is the area to the right of the test statistic. So we're looking for this area over here. We're looking for that area. So all we have to do is find the area to the right of 2.5 on the standard normal distribution. So we come here, and we're not finding inverse norm now because we're not looking for a z-score. We have a z-score, and we're looking for a area or a percentage probability. So we're going to go to normal CDF, and normal CDF, we're going to put the left z, which in this case is going to be 2.5, 2.5. We're going to put the right z, which in this case is going to be E99 infinity, E99, and we close our parenthesis, and we get that this is equal to 0.006. So the area here, which is the p-value, the p-value, which is the area, is equal to 0.006. So we're going to use this significance level, 0.05, to either reject or fail to reject the null hypothesis. Well, since our p-value is so small compared to our significance level, we're going to reject. Anytime the p-value is less than the significance level alpha, we reject the null hypothesis. We reject the null hypothesis, all right? So in the case of number 30, the p-value is 0.006, and that leads us to rejecting the null hypothesis because it's less than 0.05, the significance level. All right, so now we're going to look at number 34. For number 34, what we're going to do, let's see, it says we have the alternative hypothesis is not equal, which tells me that I have a two-tailed test. All right, a two-tailed test because we have not equal. So I have a tail over here and a tail over here. So when I find the area that corresponds to the test statistic of 0.35, I'm going to have to double it because I not only have this tail, but because it's two-tailed, I have this tail. So in a two-tailed test, you actually have to double the area to the right of your test statistic, or to the left of your test statistic if it were negative. So now we're going to look for that area. There's actually a trick that you can use here. Because there's symmetry here, we know that the other critical z is negative 0.35. So technically, you can use either one of these two and double the answer to get the entire area. So let's go ahead and do that. Let's see. Once again, we're not using the inverse norm like we were before. we are using the normal CDF because we're looking for the area. So we go to second distributions, normal CDF, which is number 2, normal CDF, and from there we are going to plug in our left endpoint, which is 0.35, 0.35. This is the left endpoint right here. And then the right endpoint, this area goes forever into infinity. So the right endpoint is going to be E99, which we use to represent infinity. Second, comma, which gives us the E, and then 99. Close the parenthesis. And there's the area. This is our um, p-value. So in this case, the p-value is 0.36, 0.36. And when we compare that p-value to alpha, the p-value in this case is much larger than alpha. P-value is greater than alpha. Oh, actually, I forgot something here. This isn't the p-value, actually. In order to get the p-value, let's follow the table. What type of test? Well, this is actually a two-tailed test. Is the test statistic to the right or to the left? Well, the test statistic is to the right. It's positive. Positive test statistics are on the right, negative test statistics are on the left. The p-value is actually twice the area to the right of the test statistic. So this number here that we got for the area to the right of 0.35 is actually only half of the p-value. We actually have to multiply this by 2 to get the p-value. So the p-value is actually 0.73. So the p-value for this hypothesis test, the p-value here is actually equal to 0.73, which is twice the area to the right of this test statistic. And that p-value is a lot larger than alpha of 0.05. So when the p-value is larger than 0.05, we fail to reject. We fail to reject the null hypothesis. So in this case, this hypothesis test leads us to fail to reject. And remember, most values fall within 2 standard deviations of the mean. So a z-score that's only 0.35 is not even 1 full standard deviation. So it's well within the range of usual values. All right. So let's do this last one. For the last one, we have a left tail test here. This looks like a left tail test because we see the alternative hypothesis is less than. So we have a left tail test. A left tail test. All right. So we're looking for this area here. And the test statistic is negative 2.95. So let's look up here again. So what type of test? This is a left tail test. The p-value is the area to the left of the test statistic. So we just need to find that area to the left of the test statistic. So we go to the TI, and we're going to do second. Well, let's clear this first. Second distributions. We're going to do the normal CDF, and then we're going to put in the left endpoint. Well, there's no left bound to our area. So we're going to put negative infinity, which is negative E99. Then comma. Then we're going to go all the way up to negative 2.95. That's the right Z. And we are going to press enter. And it seems like that area is 0.001. Oh, very small. So the p-value here, the p-value is equal to 0.001, less than alpha. That's less than alpha, which is 0.05. Whenever the p-value is less than 0.05, then whenever the p-value is less than alpha, alpha is not always 0.05, but whenever the p-value is less than alpha, we reject the null hypothesis. Reject the null hypothesis. All right, so that's how we're going to find and use our p-value. Low p-values lead us to reject null hypotheses, okay? All right, now the last thing we're going to look at is stating the final conclusion, okay? Now, stating the final conclusion. In exercise 37 through 40, state the final conclusion in simple, non-technical terms. Be sure to address the original claim. The original claim is that the percentage of on-time U.S. airline flights is less than 0.75. So that is the claim, that the percentage or proportion is less than 0.05. Oh, sorry, not 0.05, 0.75, 75%, 0.75. That's the claim that we have here, the original claim. All right, now since that's the claim, the initial conclusion is to reject the null hypothesis. So well, let's see, the null hypothesis would be, uh, this would be the alternative hypothesis because it doesn't contain equality. The null hypothesis would be that P is equal to 0.75. So let's see. Let's go through and find our final conclusion. This is the initial conclusion. This is very technical. I don't know what you mean by reject the null hypothesis. But we want to word this in a way that a layman would understand. So we start here. Does the original claim contain the condition of equality? Well, this is the original claim, and no, it does not contain the condition of equality. It is, in fact, the alternative hypothesis, and only the null hypothesis contains the condition of equality. So the answer to this question is no. Do you reject the null hypothesis? Well, it says here, reject the null hypothesis. So the answer to this question is yes. Now it says the sample data support the claim that the original claim, blah, blah, blah. So that's what we would say. The sample data support the claim that the percentage of on-time U.S. Airlines flight is less than 75%. So we would actually put this phrase in front of our original claim. That's all you're doing. Taking the phrase from the yellow box and putting it in front of the claim. So let's do that one more time with the number 40 here. All right, so number 40, the original claim is that the percentage of Americans who believe in heaven is equal to 90%. That's the original claim. So the original claim is that the proportion is equal to 90%, so 0.9. So the proportion is equal to 90% is the original claim, all right? Now let's see, is that a null hypothesis? Well, yes it is, it contains equality. So this is the null hypothesis. The null hypothesis is that, the null hypothesis is that more than, or is that the percentage that believe in heaven is 90%. All right, that's the null hypothesis. All right, let's get you back down here. Okay. All right, so that's the null hypothesis. The null hypothesis is that the proportion is equal to 90%. Now that means the alternative hypothesis, since we have the null there, the alternative hypothesis is that proportion is not equal to 90%. So we have the null and alternative. All right, so does the original claim contain the condition of equality? Well, this was the claim. The claim was that the proportion was equal to 90%. That's the claim. So the answer there is yes, the original claim does contain equality because it's the null hypothesis. Do you reject the null hypothesis? Well, it says here in number 40 that we're going to reject the null hypothesis. Reject the null hypothesis. So the answer there is yes. So how we would word our final conclusion in terms of the original claim is, there is sufficient evidence to warrant the rejection of the claim that the percentage of Americans who believe in heaven is equal to 90%. So that's how we'd word it. We just read the yellow box and then read the original claim. All right? So that's how we word our final conclusion. You just need that chart. And here is our two methods that we're going to use for finding the conclusion, whether to reject or fail to reject. We already spoke about the p-value method a little bit. That's the method that we're going to employ, but there's a second method which uses the critical region called the traditional method, and you can take a look at that. It's actually figure 8.9. We're going to look at that, and here's how we're going to reject our hypothesis in each case. All right, so you can go ahead and read through that. In the next section, we're going to actually run some hypothesis tests, so we're going to see how all of this fits together.